everyone from London. I'm Eyal. I'm a senior data scientist in a health tech company. And yeah, I was in a similar situation last year when I was at PyData Global, and I was wondering how and if I should be learning about causal inference. So I'm very glad today to discuss my learnings. And the way I approached it is I did some research. I formed with my colleagues a study group, and together we learned the topic. And the outcome was, I feel that now I'm better both in how I analyze data and how I do experimentation. And that's something I talk about a lot with people. And I feel that if you say something for a third time, you might as well write a blog post about it. If you say it for a sixth time, you might as well submit a talk proposal. Just before I start, I want to mention that all the opinions are my own. And if you're interested in following the talk, then you'll have all the slides available here just with this link. All right, so we put a lot of trust in data. We put so much trust in data in such that we feed it to non-sentient beings to analyze it, find patterns, make suggestions upon which we make decisions. Of course, I'm referring to the powerful machine learning processes that we're all beneficiaries of. But what I do feel is that there's an overlooked question. How much trust should we put on data on its own? As a researcher, my experience shows me that I never trust my predictive models until I do a full exploratory and I understand my data. And that's one of the findings that I had from learning from Judah Pearl, who's considered the godfather of causal inference, is that causal inference derives from understanding the story behind the data and appreciating that it's as important as the data itself. And that's the main takeaway from today. More takeaways that, that you'll have is that by understanding the importance of the story behind the data, you'll be able to avoid misinterpretation of an analysis. In addition to that, you'll learn about a very powerful yet simple to understand tool called graph models, which will enable you to visualize the story behind the data. And that's what most of the audience will take away from today. For those who are really interested in taking it one step further, I'll provide resources that I found useful in my journey into learning the topic. And this talk is not only for the technical, it's for anybody who makes data-driven decisions and is interested in going beyond correlations and to cause and effect, in adding cause and effect into their analysis. And there's no much requirements required, maybe high school statistics, but I'm very visual oriented. I've been doing data analysis and predictive model for over 15 years on various types of data sets, to name a few, in cosmology, biology, and now healthcare. And what I found odd is that, or rather limiting, is that as Homo sapiens, we have been improving and developing ourselves using cause and effect in our everyday intuition. But for some reason, historically speaking, as analysts, we haven't been doing that. And it's time that we should. And so the way we're going to learn about this is we're going to climb Judah Pearl's causal ladder. And the way I structured it is through an agenda in which I'll present the problem of being in this current bottom rung. And by that, I mean, what's the limit? When we do correlation analysis, why is that limiting? And we'll talk about that also in this next part, in which we'll discuss how we might be able to misinterpret our data. So through something called Simpson's paradox, we'll identify it, we'll resolve for it, and by that we'll be climbing up to the second rung. In addition, I'll present the graph model tool, in which you'll be able to visualize the story behind the data, and then we'll summarize how much you climbed up the ladder and what other steps you should do in order to further progress your understanding. I haven't said the word Python yet. I will show two very short demos using both Streamlit and PGMPy. In addition to the slide deck, you'll have links to all these demos so you can play around with and grab me for a chat later. Correlation does not imply causation. You know that phrase, but why? What does that mean? And how is it limiting? And so what we'll see in the next few slides is that by limiting your analysis to correlations, you might be either inconclusive or even worse, you'll get misleading conclusions. I'm going to demonstrate this through a few made up but plausible experiments or scenarios. In this first one, you'll see, let's imagine that a city council wants to reduce the rate of drownings at their beaches. And so to that extent, they want to know how to optimize lifeguarding duty. So let's assume that they don't know how to do that, and they want to feed all the city data that they have available to a machine so it can tell them how should they base their scheduling. And so the machine, it doesn't understand context. It goes through all the data, and then what it finds is that a very important parameter is ice cream sales. Why is that important? Because it sees here that there's a very strong correlation, which we can visually see. But does that mean causation? Well, we know that most likely not, right? If there isn't a shipment for ice cream, let's say there's a problem in the delivery, that's highly unlikely to change the drowning rates. So how do we overcome this? Well, what we actually know is that there is a common cause, which is the weather. And without that, we have that spurious correlation that we saw before. But when adding that component and accounting for that story behind the data, we can see that looking on sunny days, there's no correlation, and on chilly days, there's no correlation either. And so by understanding common causes, we'll be able to resolve for spurious correlations. Of course, that was a very simplistic graph. Reality is more nuanced than that. And so, for example, on this side, you'll want to understand supply and demand. And on this side, well, of course, you want to introduce the intervention variable, the treatment variable, which is related to the drownings and everything that leads up to that. So that's a first example. Another example is, let's say we think of an engineer who wants to improve a fire alarm system. What sort of experimental data should they be collecting? Well, of course, they want the fire temperature and the distance from the alarm. But actually, that's a good start, but there's more to that. Actually, there's no such thing as a fire alarm. The alarm is detected by the smoke, and the smoke is considered a mediator variable, and that serves as a proxy for the fire. Imagine, for example, that we're ventilating smoke out of a window, and then there won't be any alarm by the sound. Alternatively, if there's no fire, but there's only smoke, then the sound will go off. So in addition to the fire variables, you'll also want to measure the density of carbon monoxide. Sticking with the theme of smoke, but now in regards to cigarettes, well, now we know that smoking cigarettes will enhance your risk for lung cancer, right? We see that labels in cigarettes, but we didn't know this back in the 1950s. Back then, you had researchers find correlations between the two, but they were inconclusive about what they could determine based on that. What kind of decisions could be made. So for example, the tobacco industry, they could come up with a story behind the data and saying, hey, maybe this is also a spurious correlation due to genetics causing both increase for appetite for smoking and risk for lung cancer. An alternative story is that maybe lung cancer is impacted by both, but there's no real way to disentangle between them because DNA sequencing was not possible until the year 2000. So how it was actually resolved for was identifying a mediator variable in the form of tar in the lungs, assuming that it isn't generated by one's genetics, then it's impacted by smoking, which in turn, that's what causes the lung cancer. And so what we talked about so far is by limiting yourself to correlations, you might be inconclusiveness in your analysis, but even worse, you might actually be misinterpreting your results. And that's a very dangerous place to be. So it's such an important topic that I'm actually going to dedicate the next topic to it, Simpson's paradox. And as a disclaimer, I'm going to use an imaginary but plausible example data. And for simplicity, we're going to assume that it's statistically significant. Another disclaimer is I'm going to do something that may be considered highly foolish as a presenter in the sense that I'm going to confuse anywhere between 95% to 100% of the audience. But the reason that I feel that it's worthwhile, and note that I'm going to do this for about 10 minutes. The reason it's worthwhile is that there's a huge lesson to learn here, and it will be memorable. Hopefully, it will be enjoyable. But the main reason I'm doing this is because you might be misinterpreting your data right now when you're not aware of it. And so we'll do this through an example of a made-up pharma study in which they're looking into measuring the benefit of a drug that they're developing. So they set up a random controls trial. And what I mean by that is that they have sick patients that are equally distributed amongst a control group and a treatment. And looking at the results, we can see the treatment group recovered 58% of the time, but that's less than the control group. So we see this gap over here, and that's all fine. But now let's look at actually cohorts at different subsets. So we'll look by gender, and then we see something interesting. We see that males, actually the treatment group recovers and with an absolute 10% higher than the control, and the females have the same absolute 10%. Also, we see that the females recover in both cases more than the males. So it's the same data, but oddly we have contradicting conclusions. And that's what the Simpson's paradox is. It's when you have a contradiction between the result of your population to your subpopulations. In the following slides, we'll see that this isn't actually a contradiction or a paradox, but it's rather misinterpretation. And so so now let's look at deeper in the numbers, and that way we understand what are we actually missing, what are we misinterpreting here. So here I'm just summarizing what I said before, the contradicting conclusions by focusing on the population at large and at the cohorts. And here I'm presenting also the numbers of the cohorts. So here you can see the 50 versus 40 and 90 versus 80. I'm a big fan of visualizations. And so any visualization that shows such contrasts is very useful. So here I'm doing the treatment minus control, where the population is minus 14 and the cohorts is at plus 10. I love this other visual that really brings this home. It was designed by Mark Platz. He's a data scientist that I met in PyData Global of last year. And so I'm borrowing this idea from him, in which what he does very nicely is how he separates between the different groupings. So first of all, he separates between the control and the treatment group. The horizontal axis is the recovery rate, and the vertical axis is the number of participants. And then you can identify in the control group, for example, there's two different groups in which one recovers an 80% rate, and they're actually 80% of the control. And then the remaining 20% of the control recover at a 40% rate. And so their mean is this red line. And that's what we call recovery rate of the control group. And we do similar thing for the treatment. And this is where the minus 14% is, right? Treatment minus control. But the beauty of this visualization is now we'll focus on the cohorts. Now we're color code for them. And now you can see the females, you see the plus 10% here, and the same thing for the males. Same data, but different approach. So what's the truth? Should we go by the population or the cohort? Well, that depends again on the story behind the data. The story behind the data here is that both the outcome of the group, both the outcome and the group, placebo or drug, depends on gender, where gender is an independent variable. And hence it's what we call a confounding variable. And what we should do is we should control for that. And that's something that we haven't done over here. So this renders this outcome actually as meaningless. And to be meaningful, we have to control for that. And just to highlight the fact that the gender is a confounding factor, those with hawk eyes notice that males were 20% of the population and females were 80%. Okay, so in order to adjust for this, for the confounder, first, we have to be a bit more rigorous in how we determine our metrics. So when I say treatment minus control, that's what we call the risk difference, where just mathematically we write with conditional probabilities. It's the difference between the recovery rate of the two groups, the treatment minus control, and these are the risk differences that we saw for each of the population and the cohorts. So what we have to do in practice is we have to do weight adjustment. So what we do is we create this meaningful average causal effect metric, which what it does, it takes the weighted mean of the risk differences of the different strata. And by that, I mean the male and the female, assuming the weights are 50% per the group. And so then you get the result that you expect, the 10%. And here's just the visual. Again, this is meaningless, and these are meaningful. As I said before, you're most likely to be confused. That's fine. I demonstrate this to experienced analysts and data scientists, and all of us get confused. I'll be the first to admit it took me weekends to fully understand and appreciate this, playing with numerous examples in a Jupyter notebook. And with time, I found what was useful for myself is a web app that I use Streamlit for. And so you have it available here if you want to play around with it, but I'll just show a quick demo. Yeah, and so here actually is the same example in which I just coded up. So you have all the data, you have the visuals, and here's the Platts figure. And yeah, so what I like to do is in order to understand these things, I change the variables around. So what we'll do here is we'll look at one of these cohorts, and let's say that the data was different. Let's say that there was no impact for one of the genders. And so that's what I'm changing over here. And so here you can see that now they're aligned. And so that means the impact for the males is 0. With the females, I didn't change anything. That still is 10% over here. And so this is a meaningless metric, so -16. So we want to calculate the ACE. So I'll give you like 2 or 3 seconds. Think between 0 and 10, what should the ACE yield, right? So that's what we expect from an average person, average male, male or female. Well, if you guessed 5%, well, that's correct, right? That's the mean between 0 and 10. So that's just one of many examples that one can try to use to play around with in order to internalize, to understand Simpson's paradox. Another way to understand it is through this sort of visual in which the equivalent of Simpson's paradox using continuous variables is Lord's paradox. So what do I mean by that? Instead of the drug and placebo binary variable, imagine that you have medicine in milligrams. And instead of recovered or sick, imagine like a continuous health score. So if you don't have any cohort data, then for example, you can see like a 20% correlation here, and you can draw this red line. But if you add the story behind the data, like the cohort information, you'll see actually that you will learn actually that adding medicine in milligrams is deleterious in the outcome for men, boys, girls, and females. And so, yeah, so I appreciate that's a lot to take in, and it's fine to be confused at this stage. What should you take home from the Simpson's paradox? Well, the main takeaway is that anytime you identify that you have a contradiction between the result of a population to its cohorts, the reason that's important is that if you have that case, if you have that scenario, you have to be very careful not to misinterpret the data and get wrong conclusions. What should you do? You should identify the confounding factors and control for them. For those who are interested in taking causal inference to the next step, I highly recommend mastering Simpson's paradox. So we're actually going to continue on this note of controlling for confounding factors, because that's a big part of causal inference. And the reason that's important to highlight is the fact that sometimes you'll have researchers talk about a shopping list of many parameters that they're controlling for. But you have to be critical about this and ask yourself the question, is that justified? And that's a very hard question to answer for. And what you want to do is actually introduce something called graph models, which helps you visualize the story behind the data, and then you'll make more educated decisions about how to decide which parameters to control for. And that brings us to the next step in the causal ladder, in which we'll use the graphs to visualize the story behind the data. And Judah Pearl correctly says that this is that it's the missing vocabulary in order to articulate causal inference, which is missing from most statistics textbooks. So we'll talk about this. And it's actually, in addition to being a very powerful tool, it's actually a very simple one. It's so simple that you actually know what it is, because when I talked about, let's say, the smoke detector, I actually used graph models there. And by the arrows, you understood what was going on. But here I'll be more formal in introducing it. So what we do is that each variable is a node, and any two nodes that are connected, there will be, any two nodes that have a correlation will have an edge between them. To add causality, we turn an edge into an arrow, which tells us which node is listening to which. And just before here, you can see, for example, A and B are independent, C depends on B and D depends on all of them, where they have a cyclic interaction with C. An even more simple graph is called a DAG, in which the essence of it is that starting from one parameter, you can never find the cycle to go back to it. For example, you start from A, there's no flow of information that goes back to A. And the reason this is useful is that we're able to help you describe how the data was collected, and you can write down your understanding of which parameter causes which, who listens to who. And the reason this is powerful is that you'll be able to design both better experiments and have better interpretation. You'll be able to make causal conclusions from your data. And so we'll actually go back to the Simpson's paradox, and it's very simple to understand actually with the graph model. So this is the setup that we had from before, in which you'll notice gender is independent, outcome depends both on gender and group. And the reason that the paradox arises is because of this, is because our treatment variable, the group, depends on gender. How do we resolve it? Well, we do what's called graph surgery. And what we do is we cut off, we eliminate this arrow. How can this be done? It can be done in two fashions. Either we account for the confounding factor in the randomized controlled trial in advance. That is, but mind, that's both expensive, but it also can be, in some situations, impossible. Here we're talking for simplicity about only one confounding factor, which you might have many more. And so the beauty of a causal inference is that we can apply it, the same concept, to observation, what's called observational data. That's something that's much more accessible and much more cheap. For example, we talked about the average causal effect, the ACE. And so that's the same thing in which we, we did the graph surgery there. We adjusted for the gender. Critics of causal inference correctly point out about subjectivity, right? We're building a narrative behind the data, so that's adding subjectivity. As a data analyst, my experience is that as objective as I'd like to be, I always have to make subjective decisions at certain stages. And the challenge is to make sure they're sound and reasonable. For example, if you have a distribution with two modes, well, you don't want to naively take the mean or the median, but you want to understand the story behind those modes. And in the same regard, yes, in the graph model, you're going to make assumptions, but the beautiful thing that beyond the scope of this talk, but what you learn in causal inference is that you'll be able to empirically test the graph in certain regions for the causal relationships between the nodes by identifying the dependencies between the parameters. Causal inference is not always possible. It requires many assumptions. It's beyond the scope of this talk to go through them, but my understanding is that the most important one is called ignorability, and that's and what that means is dealing with all the confounding factors. And that's why I'm putting an emphasis on this. For example, we looked at the drowning rates example before. This was what's called, in terms of a graph model, it's something called a fork situation, in which without, so here we're confounding for Z, but without that, we saw that we have a spurious correlation, and that's what we wanted to resolve for. Alternatively, there's another graph model that's called an inverted fork, in which we have something called a collider, and actually it's the opposite than before. It's beyond the scope of this talk also, but it's interesting to point out that by confounding for the for this variable, you're actually going to generate spurious correlation between the variables. And so if you're interested, my slide deck is available. And here I show a nice example of a light and two switches in which if you control for the light, you'll cause a spurious correlation between otherwise independent switches. So just to summarize, the essence of causal inference depends on your ability to control or not for parameters. We talked about common causes in forks. Before I talked about mediators in chain, right? Remember smoke and tar in lungs. And beyond the scope of this talk is colliders and something called instrumental variable. So we're nearly at the end. Let's see how far we went in our journey of climbing up the causal ladder. And so we started by identifying the fact that by limiting ourselves to correlations, we're taking a very passive approach. And the worry behind that is that we might run into misinterpretation. For example, spurious spurious correlations, or Simpson's paradox. We resolved the Simpson's paradox by doing something that now I'll call as do algebra. What we did what you saw in practice here, one flavor of that is we controlled for a confounding factor, right? In a manner called ACE, the average causal effect. And the reason this is powerful is we can now do causal inference for subpopulations and reflect that on the population at large. For example, looking at a drug, seeing if it's beneficial, for example, for a female between ages 35 and 45. But even more powerful is going to the third rung, in which what you'll be able to do is to do it for an individual person, say your mother, your sister, or your cousin. And that's by means of something called counterfactuals, in which I don't have time to talk about today, but generally speaking, it's setting up hypothetical conditioning in asking what if statements. What if the condition was a bit different? What would be the impact of that? So that's very powerful. But as I said before, it's not always applicable. It really depends on circumstance. For example, if you have simulated data, it's much more likely that you'll be able to do it. With most real-world data, you'll have the challenge of not being able to rerun real-life scenarios. And so that means a lot more assumptions are required. But regardless, my learning state that what you want to do is in any situation, evaluate the applicability of causal inference. In that way, you'll be better both in how you design for experiments and analyze it. To further motivate, the Nobel Prize for Economics went recently to researchers that help further develop our understanding of causal inference. So what should you take away home with you to share with your partner, your friends, your colleagues, is the fact that when you have data, you don't want to trust it on its own, but you rather want to understand the story behind it. How was it collected? What's the causal relationship between the parameters? That way, you'll avoid misinterpretation of the data. I introduced the graphic models as an easy to understand yet powerful tool to visualize the story behind the data. Those who want to take it to the next step, they'll be able to, I suggest, master Simpson's paradox, then do algebra, counterfactuals. That's the way it works for me. Alon Nir, who's giving a talk later in the conference, he'll talk about actually counterfactuals. Him and I, we're aggregating resources that we find useful. And here I'm just highlighting a few of them. For the layman, I suggest the book of Why by Judah Perel. For the study group that I mentioned before, we actually used his primer book that's very useful. With my remaining time, I want to just highlight something about PGMPy, which I found useful for the reason is that they're using do operations. And so what I have publicly available, I made a notebook in which you can actually go through my Simpson's paradox example right over here, in which you'll be able to learn how to generate the story behind the data to calculate things like ACE, like the ACE parameter. So I want to thank my colleague James Baker, who is a true doodle master who created these visualizations. I want to thank Streamlit, all the Streamlitters out there. Thank you very much for helping me put my ideas into quick production. I'll skip this. And yeah, so obviously we're out of time. Hit me up. I created a special Slack channel to continue the conversation there, and stop me and gather for a chat.
Okay, thank you so much, Eyal, for being with us. Thanks, everyone, for joining us. Unfortunately, you don't have time for questions, but you can just post your questions in the Talks channel, or you can just go to the Gather and continue the conversation. Thank you so much for being here with us. Thank you.